This is lesson 5.1 on systems of linear equations, substitution. So in this last unit of the class, we're going to be looking at systems of equations and matrices. So matrices are actually a tool that we can use to help us solve systems of equations, but they're also interesting in their own right. But before we get to matrices, we're going to spend some time working with systems of equations, systems of inequalities. So we need to talk about what we mean by that word systems. So when we're talking about a system in mathematics, outside of mathematics, system often means something else, a way to work things. We mean something a little bit different here. When we talk about a system of equations or a system of inequalities, which we'll mention later on, we basically just mean a collection of more than one equation. So a system of equations is going to be a collection of two or more equations. We will talk about a solution or solutions to a system of equations. What that means is if we find a solution to a system, that means we have found values for the variables where when we plug in those values, every single equation in the system comes back true. So a solution to a system of equations will satisfy all of the equations simultaneously. They all have to be true at the same time. Now we are going to focus on linear equations, so systems of linear equations. So let's remind ourselves what we mean by linear equations. A linear equation is going to be one in which the powers, our variable parts, are always going to be first power, first order terms. And what we mean by that is individually the exponents of the variables are always power 1, and we never multiply them together. So we will never see square root of x, we'll never see x squared, we'll never see y squared. We're never going to see x times y also. So we don't multiply our variables, we don't raise them to powers other than 1. Now one important thing to note is as we introduce more variables, which we will, linear equations don't necessarily describe lines. Now, a linear equation involving two variables, yes, that describes a line. If we have just an x and just a y, that will describe a line. But as we introduce more variables, our shape it's still nice. We consider it a nice shape, but it's technically no longer a line. So for example, if we have a linear equation in 3 variables, that's going to describe a plane. A linear equation in 4 variables, that's weird. But it's basically going to be the equivalent of a plane in 4 dimensions. So in some sense, a line is a plane in 2 dimensions. So if we had a linear equation in 4 variables, that would be a plane in 4 dimensions. Again, we can't really think like that too easily. Don't worry about it. You won't need to. We're not going to see 4 variables. Don't worry about it. But none of these, or a lot of these things, are not technically lines. So don't let that throw you off. Linear just means that we're dealing with first order terms here. Now the technique for solving a system of linear equations that we're going to look at today is a fairly basic technique called substitution. I only recommend using this technique when you're dealing with a pair of equations with 2 variables. So a system of 2 linear equations in 2 variables. Here's how we do it. Take one of your equations, it doesn't matter which one, and solve for one of your 2 variables. It again doesn't matter which one. You can't go wrong at this step. Once you solve for that variable, look at the other equation. You're going to substitute in what you solved for into that second equation. Once you do that, you're going to realize that you only have one variable left in that new equation. Solve for it. It's going to be a nice linear equation. It's going to be the type of thing that hopefully we could do in our sleep by this point. You're going to get an actual numerical value back for that variable. Our last step is to take that number, plug it back into the substitution that we found in step 1 to find the value for the other variable. We've got a value for both variables. It's going to make both equations true at the same time. There's our solution. We're done. Now this is going to make a little more sense when we see it in action, but we're always going to go through these same 4 steps. Solve for one variable, substitute in, solve for the new equation, resubstitute back into what we found originally. So we'll find values for both variables. That's our solution. We'll be done. So we'll see a couple of quick examples of what we'll see on a drill, and then we'll look at a word problem where we can use a system of linear equations to help us solve it. Okay, so here's what a system looks like. So notice we have two different equations here, and notice here we have these curly braces, this curly brace that's kind of grouping them together. We won't always see that. I'll try to include it to be consistent, but there are some folks, some books that choose not to include that. It's really not a make or break thing. All it's doing there is just reminding us that this is a system. We're considering both of these equations together. So again, if you see it, great. If you don't worry. When we see two equations together, or 3 or 4 or 5 equations, we're dealing with a system. We want to solve them all simultaneously. So I'm going to call this first one up here equation 1, and this one down here equation 2. So what I would recommend doing is pick one. It doesn't matter which one. Sometimes you're going to see that there's one equation for which it will be easier to solve for one of the variables, but it doesn't matter one bit. You're not going to screw things up at this point. I'm going to go ahead and take equation 1 and solve for x. So I'm going to subtract 2y from both sides, and that will give me x equals 5 minus 2y. Okay, what I'm going to do now is I'm going to take this and plug it into equation 2. Make sure you plug it into the other equation. Do not plug it into the same equation that you just solved. You'll be running in one big circle if you do that. So I'm going to take this and plug it into my other equation. So instead of 2x, I know that x equals 5 minus 2y, so I'm going to put 5 minus 2y instead. Then the rest of the equation stays exactly the same. So notice I only have one variable now, just y's. So this is a simple linear equation. I can solve this lickety-split. So simplify 10 minus 4y plus y equals negative 2. So that's going to be 10 minus 3y equals negative 2. All right, I'm going to subtract 10 from both sides. So I have negative 3y equals negative 12. Then I divide by negative 3, so y equals 4. Okay, now to get my x value, I'm going to take this and plug it back in way up here at the very beginning, where I substituted in, where I solved for x before substituting that in. So I know that my x is going to be 5 minus 2y, but I now know that y is 4. So we get x equals 5 minus 8. So x equals negative 3. So my final answer is x equals negative 3, y equals 4. Normally when we have more than one variable that we want to state a value for simultaneously, we're going to use ordered pairs, just in the same way that when we're talking about our coordinate plane, we use ordered pairs. So here we would say that our answer is negative 3, 4. Now real quick, you won't need to do this for a drill, but just to demonstrate what we mean that this is a solution. Let's take these values and plug them back into equation 1 and equation 2. So x plus 2y equals 5. So x I know is negative 3 plus 2y, y is 4, equals 5. This is my first equation. So I have negative 3 plus 8 equals 5. Sure enough, that's true. So this satisfies equation 1. Let's try out equation 2 now. So 2x, so 2 times negative 3 plus y, y is 4, equals negative 2. 2 times negative 3 is going to be negative 6 plus 4 equals negative 2. Yep, that's true. So this solution here satisfies both equation 1 and equation 2. So this is a solution. Once again, for the drill, you don't need to do this. If you want to, if you're unsure if this is a correct answer, feel free to, but it's not an expected part of your solution. All you need to do is this part here. Here's another one. So solve this system. So again, I'll call this equation 1 and equation 2. I usually number or otherwise label my equations just to help me keep track of which one's which. Because remember, you don't want to substitute back into the same equation that you solved for. I have a habit of just taking whatever comes to me first, so I look at equation 1 and see it's going to be pretty easy to solve for y, so I'm going to do that. Let's subtract 3x from both sides. So if I do that, from equation 1, I get that y equals 7 minus 3x. So I'm going to substitute this in to equation 2 right here. So x minus 4y, but instead of y, I'm going to put what I just found, 7 minus 3x equals 1. So once again, first equation I solve for y, then I substitute that into the second equation. I've got one variable now, so I solve. X minus, let's see, we get 28 plus 12x. Don't forget to distribute your negatives correctly. Common mistake, it unfortunately wreaks havoc on your solutions. So negative 4 times this, make sure you distribute the negative correctly. So we've got 13x minus 28 equals 1. So let's add that 28 to both sides. So 13x equals 29. So x is going to be 29 over 13. That's not a terribly pleasant answer, but it's okay. Sometimes we get nice answers back, sometimes we don't. So what we do now is we're going to take this and plug it in right up here to find what our y value is going to be. So y equals 7 minus 3 times x, but I know that x is 29 over 13. All right, so I gotta think here. I gotta use my fraction abilities. So I need to get a common denominator of 13, I know. Let's go ahead and multiply things out. So this is going to be, let's see here, 3 times 29. Let's do that real quick. So it's going to be 27, 2, 6, 8, 87. So 87 over 13. I need to get this with a common denominator of 13. So I need to multiply 7 by 13. So it'll be 21, 2, 7, so 9. So I have y equals 91 minus 87 over 13. So y equals, that's going to be 4 over 13. So remember, we write our final answer as an ordered pair. That ordered pair is going to be 29 over 13, comma 4 over 13. So once again, sometimes we get nice answers, sometimes not so much. When you get nasty answers back like this, don't let it bother you too much. It happens sometimes. It in fact happens fairly frequently when we're working with systems of equations. So just because we've got an unfortunate looking rational solution here, it's still perfectly acceptable. It's still perfectly fine. We do have to do a little bit of extra thinking, a little bit of extra work here, but nothing out of the ordinary. It's fairly routine calculations. So do be careful. Do pay attention to what you're doing here, but don't freak out when you get rational answers like this. All right, we're going to use this technique to help us solve a more complicated word problem. It seems a little intimidating, but once we break it down into a system of equations, it actually falls out into our lap fairly easily. All right, so let's consider this word problem. So tickets to the school play cost $5 for students and $8 for non-students. So how many tickets of each type were sold if 32 tickets were sold for a total of $199? So notice in this problem we have two unknowns. We have the number of student tickets that were sold and the number of non-student tickets that were sold. So let's identify our variables. Let's let S equal the number of student tickets. S is student tickets, and then N, let that be number of non-student tickets. All right, so S is number of student tickets, N is the number of non-student tickets. So let's see here. We know two pieces of information here. We know that there were 32 tickets sold. So that tells us that S plus N equals 32. The number of student tickets plus the number of non-student tickets is going to be 32. We sold 32 total tickets. Next, we know we raised a total of $199. Given that student tickets cost $5 and non-student tickets cost $8, we can conclude that 5 times S plus 8 times N equals 199. So notice we have a system of two equations here. So what we need to do is solve for one of our variables up here, substitute it into this equation to solve for one of the variables, and then plug it back in again to find the value of the other variable. So I'm going to take this equation here and solve for S. So if I subtract N from both sides, I get that S is 32 minus N. So I'm going to take this piece of information here, plug it into my second equation. So 5S instead of S, I'm going to write 32 minus N plus 8N equals 199. So 5 times 32, let's see, it's going to be 150 plus 10, so 160 minus 5N plus 8N equals 199. So 160 plus 3N equals 199. So let's subtract 160 from both sides. So 3N is going to be, let's see, that's going to be 39. Finally, dividing by 3, N is going to be 13. So I now know that 13 non-student tickets were sold. I now need to find how many student tickets were sold. I'm going to take this number and plug it in right here, the thing that I used to substitute earlier. So S equals 32 minus N, but I now know that N is 13. So S is going to be, let's see here, what is that, 19? So our final answer is 19 student tickets and 13 non-student tickets. So when you're solving word problems, a good rule of thumb is to always make sure you answer the question. So here we're asked how many tickets of each type were sold. So we need to give the values for both of our variables. If for whatever reason we were only asked the number of student tickets that were sold, we could just put 19 and we'd be done. So always double check the problem, always make sure that you give the correct final answer.